helpful for the final. Some of
Mm-hmm.
this will just be helpful on your future employment.
That would be nice.
What'd you say?
I said that would be nice.
So first off, you classification. You have triangles. You have dots. You tell the algorithm what is a triangle and what is a dot, and it tries to find a way to separate triangles from dots. Unsupervised learning is different from classifications because there are no labels. Now you're trying to find patterns and create groups in the underlying structure of the data. It's useful for anomaly detection or creating groups where it's missing, like market segmentation. This has gotten really big, particularly in macroeconomics lately, where you start off with this very high dimensional data set, all these features, and so you try to find ways to put them in clusters, to say these are like each other. It's a very simple algorithm, and most importantly, it's great for large amounts of data where you don't have you're just looking for patterns. So often you don't have classes or you don't have explanations going in, so you just have to figure out what patterns exist. Real world machine learning is highly dependent on mass amount of data. This means cloud computing, databases, efficient algorithms, and GPUs. Companies don't want you to analyze data anymore. They want you to build things that users interact with and exist in the real world. This has been really a trend for as long as I've been in the field. It used to be you'd build, so there's still a lot of jobs where you build an algorithm that sits on a shelf and it analyzes data that never changes. Finance is sometimes like that, but more and more, especially with deep learning, you're seeing this move towards having algorithms that work with users and are working with data as data is coming online. So now, instead of having something that you work with once, you create a presentation on it, and you're done forever. Now you have something that you want to work in the app, which is, kind of scary. It's a real life thing. And this is not something they teach a lot in schools, is how to build things that work with data that just isn't on your machine, but in a database. And that's going to need to work continuously rather than just one time. Reinforcement learning has been a big movement in data science. It's always been kind of cool, but it's never found any particularly valuable uses. It's moving towards more interesting uses over time, particularly in economics. I think it's the topic of machine learning most likely to have a major impact in the economic profession because a lot of what economists do is very similar to what you see in reinforcement learning. There's a tremendous view of potential synergy there, and multi-agent reinforcement learning is actually highly similar to game theory. When I took a course on reinforcement learning, the lectures were the lectures at the end on multi-agent reinforcement learning were really game theory focused. K-means is an unsupervised learning algorithm for dividing highly dimensional data points into clusters. Computationally intensive, but easy. Oh, sorry, keep going.
No, go ahead. Go ahead. No, I was just
Easy
my mic.
heuristic algorithms. It's a great place to start to find patterns in your data. So here's what k-means looks like visualized. You have these nice little decision boundaries here where you're separating the data, and you can separate the data into as many clusters as you want, though you really want to rely on what clusters actually exist. So giving a set of n-dimensional observations, so giving data that, once again, looks like this, very wide data. There's a lot of different variables. K-means clusters partitions them into I less than or equal to n different sets. So one way to do this would be to draw a circle and say, that's my cluster. There's only one, and there is she. But you can generally do better than that. And then you can create several different clusters and say these are people who are like each other. So maybe these people, K-means is often a really great way to start. Is you start off by creating clusters and you say, well, what makes these people similar? I have these clusters. What makes people similar? And now you can say, well, actually, these people are renters, or these people are owners, and these people live with someone else. So you can find common characteristics. You can later on see, oh, this variable is actually important because it creates these common characteristics. Or let's say you're working for Spotify or Amazon Music, you can say these are some variables. We don't know. We don't know exactly what these clusters mean. Maybe a cluster means Swifties. Maybe a cluster means this person likes pop. But these people have similar music, and we're just going to feed music to that's similar to similar people. So K-means minimizes within cluster sum of squares / variance. So you have the sum for all x and the sum for all clusters of x minus the mean of the cluster. That's the mean of the cluster right there. And so you minimize this and you minimize this by minimizing the variance within the cluster. So basically what this means is you're trying to find points that are really close to each other. You don't want points that are far away from each other. You want points where if you want points where in the cluster the difference is larger than the distance between, or sorry, in the cluster the distance is smaller than the distance between the clusters. So you want small distance between the clusters and you want small distance within the cluster, high distance between the cluster. You want to minimize within cluster sum of squares. So random initialization, here's the algorithm. You have a bunch of points. And then now you choose a set of points for initialization. You assign points to a cluster based on the closest. So you find the distance between all the points and both clusters, and then you assign the points to the closest cluster. So basically, you find the distance between all of them, and then you have now a decision boundary line. And you start there, and you are probably able to do better. So you start with a couple starting points, and then you assign all the data points to the clusters. You have this dividing line, and now you reset the cluster to the mean of the data points. So now you say, well, we didn't do as well as we could here, so now we're just going to say that the new clusters are here and here, because those are the means of the clusters here and here. Well, now we reassign the data and the data of the clusters, and maybe we assign new cluster data. And so now we move the centers again. And we keep doing this. We keep moving until we get to really good centers. And the algorithm terminates when the wind, and then cluster sum variance stop decreasing. So this right here stops decreasing. You now no longer are decreasing the variance of the data, or the assignments no longer change. You keep moving you moved a couple times, and you find that the data are always assigned to the same points. So the algorithm no longer continues because the points are no longer moving, and then now you have your clusters. Interestingly enough, kind of uniquely amongst most algorithms of machine learning, K-means results in different results every time. It is actually shown to converge. You can prove relatively easily that will converge by basically you assume that the way you prove this converges is you assume that the variance that you can pick a point as a starting point for which the variance will always increase. You can always show that there will always be a point at which the variance stops decreasing. So it's very easy to show that this converges, but always converges, but it doesn't always result in different results. So when you run k-means, you have to decide. I'm going to do this a few times to make sure that whatever results I get are not just an anomaly, and they're the actual clusters. Another important feature of k-means is the elbow curve. So you choose clusters based on the inflection point of what's called the elbow curve. So you're looking for a decrease in the sum of squared errors, and you'll choose a point for the clusters either here or here. Because after here, adding an additional cluster is not all that helpful. You definitely don't want to go with one cluster because there's clear evidence that there's decrease in sum of squared errors with adding the second one. You may want to go to the third because there's a little bit decrease after the third. But after this third one, there's not that much help there. It's sort of leveled off. So when the decrease is leveled off, that's when you know that you have enough clusters. You could, in theory, have as many clusters as you have points, and then you have a very unuseful algorithm, and it wouldn't do very much. So K-mediods is very similar. You greedily select K of n data points to minimize cost. So instead of initializing to a random point, you initialize to a particular data point. Then you associate, and then you choose it specifically based on a measure of centrosity, usually based on the median of all the data points. You choose data points. You associate the data points to the closest medioid by any distance metric. Consider every non-medioid point in the medioid and pick new centers based on ones that minimize cost. You choose a new point, you reassign the points, and eventually you end up with a particular point that terminates. If cost stops decreasing, you can also terminate. And what this does is speeds up k-means just a little by making sure that the center is always going to be a point. Minimizes pairwise distance rather than variance. So K-mediods is more robust to outliers. Cloud computing resources pool the power of individual computing resources simultaneously. Cloud computing runs many algorithms parallel on large amounts of data, useful for creating models that are put into operation. Seawolf is SVU's cloud computing system. Seawolf allows machines to run tasks in parallel, valuable way to train large models. Very often in the field, you might have to deal with the AWS or Google Cloud Platform or Oracle or Microsoft's Azure. These have become incredibly powerful over time, and they become money sinks for companies. So it's always very valuable to learn how to think about clusters and how to think about working on not just your personal machine, but something more. Graphical processing units speed up training of neural networks. They're good at performing certain tasks repetitively, and trained networks can much faster. These are different from CPUs or what you have on your machine, in that CPUs are good at a bunch of tasks. GPUs are good at one task. Best neural networks are trained on servers and GPUs. If you have a belief that neural networks might be in your future, I would encourage you to look up how to use GPUs through Google Cloud and maybe run some GPU stuff using sklearn or sklearn or Hugging Face. Now, databases store information on such servers. SQL allows databases to talk to each other and the internet to talk to itself. Structured query language exists to create and query databases. Hey, MD, what's going on?
Yeah, so I have a question about SQL.
Yeah.
So when I went to like look into SQL, I saw like there are different types of SQL databases. So there's like MySQL, Postgres, yeah. So I was wondering, among these like different SQL databases, which one is like the most I guess standard one, or like the most common one that you would
Usually it's a
recommend?
MySQL thing. It depends on where you're working. Um, some places use a lot of Postgres and some places use a lot of NoSQL, but
Mm-hmm.
SQL, usually you can do very well with starting off with MySQL. And the reason why I say that is that we're economists. We're
Right.
not dealing with a lot of unstructured, very weird data.
Mm-hmm.
So tends to be that the databases we deal with are more numerical. And so normally MySQL or Microsoft SQL Server Management Studio, very simple commands, very powerful for dealing with the kind of data economists normally deal with.
Okay. Thank you.
So yeah, SQL dramatically improves the efficiency of dealing with large amounts of data. So how to write an SQL statement? SQL is an incredibly simple language. So you start with a select. So select gives the variables you want to select, maybe does a transformation of them like min, and you can also change how you want to display the variable as old as work from, you changing how you're displaying. And then from, you're saying the table that you're choosing from. If you're having a multiple table structure, maybe it's uh, db1 dot prod dot artworks. So you just add dots, and that allows you to go between levels of tables. On artworks.artist.id equals artist.id. So this is a join. So you're joining artworks with artists. Yes.
For the different databases, is the syntax the same, or is it different for different databases?
It can be. So this syntax is used everywhere. This is
Mm-hmm.
You're always going to use this syntax when you're writing SQL.
So like select from join. So these are for like universal syntaxes
Yes.
basically.
This is the basic structure of pretty much every SQL query.
Okay, okay. So I guess if you're like going in depth, then I guess the syntax will be a bit different for different databases.
Yeah, you'll write the query differently, but the syntax is the same.
Oh, okay. Oh, okay, okay, okay. That makes sense. Right, right, right.
So
Okay, that.
join, there are a couple of ways to join data in SQL. They're not all using join. Basically, here you're joining artwork and artists, but using artworks.artistid equals artist.id. So you're combining artworks and artists by combining artwork data with artist data on this one common identifier.
Mm-hmm.
And now you're choosing specifically where title equals Mona Lisa. So you're getting information about the artwork and information about the painting uh, for a painting called the Mona Lisa. And you're getting the minimum year. It's the oldest Mona Lisa with year And then you're grouping, I guess this is probably database of articles, you're grouping them by name, and you're finding year less than 700, and then you're ordering them by minimum year. So whatever the variable year is, you're ordering them by minimum. So once again, select, you choose columns, from, choose table, join the table on the column that's unique between, it identifies the data between the two tables. Filter, where filter down in the data. This exclamation point equals, that means not equal. So it's not equal to Mona Lisa. Group by records, you're collapsing all records with similar names. Filter groups, you're finding minimum year less than 700, and order by, you're sorting the output. So structure of a query, select, distinct means that you're not going to have duplicate entries. Table 1, this is an asterisk or a joker character. That means you get everything. Table 2, asterisk means you get everything. From table 1, join table 2 on matching condition, where, and then you have a constraint, group by some column, order by column, and then limit restricts the number you get. So these are SQL joins. This one here is a left join. You get everything from A, and including what's in B. You can also have a right join. So now you get everything from A or from B that's not, or including what's in A. So left join, everything from A, including what's in B. And you're adding in any columns from B. Right join, everything from B, and also adding in some columns from A. Inner join, you only keep a record if it's in both A and B. And then you can also have a join where you say where A.key is null. This means you only want observations that are only in B. You can also do only observations in A. This is a left null join. You can also do a union or full outer join. This means that you're taking everything in A or B. And you can also say, I want everything that is in A or B, but not both. So select star, that's a joker character. That means you get all the columns from A, full outer join B on A.key equals B.key, where A.key is null or B.key is null. So here, all you're saying is, I want everything that is in A or B, but not anything that's in both. Aggregating functions will find an aggregate statistic based on a grouping. So it must be used with a group by statement. So you're grouping by a variable, and then you're aggregating to that variable. So you're summing salary maybe by gender to say, how much are we paying men? How much are we paying women? Average of salary maybe by race. How much are we paying white people? How much are we paying Asians? Max salary by employee ID, who's the highest paid employee. Smallest value in column, min salary by department. Maybe we're grouped by department minimum salary, who's the lowest paid salary in accounting. Count the number of rows selected. Count employee ID, group by department, how many employees work in which departments. So there's an example database diagram. This helps show you how the data sets are connected and what data exists in each of the fields. So employee ID is integer, last name is varchar. And so this shows the way to think about each of the data sets and how they're connected. There's a query exercise selecting columns, display all data in the product table, select star from product. Display the names and email addresses of customers, rename the columns to name and email. Select contact name as name, contact email as email from customer. Display IDs of all customers who made at least one purchase. No duplicated IDs should be shown. So we're doing select distinct because we don't want duplicate IDs. And then from purchase. And then display all data for customer with ID 4. Select star from customer where ID equals 4. Sample queries with aggregation. Select all category IDs and the number of products in that category. Select category ID. Count star from product group by category ID. For all customers, display the customer ID and the average price of purchases for that customer. Select customer ID, average of the total price from purchase group by customer ID. So here's a sample join. So we want to get the first and last name of the employee taking care of each purchase and ship date of that purchase. Select the last name, first name, ship date from employee, and then join with database purchase or table purchase on employee. That's that name type earlier with the dots. Dot employee ID equals purchase dot employee ID. So we have a connector, and that is the employee ID, a column that is the same in both data sets. Display the name and emails of all customers and list the names of the products they bought and the product price at the time of purchase. Include customers who haven't made any purchases. Don't rename the columns. Set contact name, contact email, product name, product item, dot unit price. So this is using this dot here to signify that you have multiple columns named that in multiple tables, but you want the unit price from purchase underscore item. From customer, left join purchase on customer ID equals purchase dot customer ID, left join purchase item on purchase ID, and you keep left joining. SQLite allows you to execute SQL from Python. I would encourage you, if you're planning on going to industry after this, to look into SQLite. It allows data to be automatically pulled into a Python environment from a database. So this is really the best way to build a data pipeline. The problem is it's really hard to get access to a database. But this is a really great way to work with Python and a database together. So reinforcement learning learns from the environment using punishments and rewards. An agent observes the state, takes an action, moves on to the next state, and observes a reward. It's very similar to many economic setups, the current forefront of machine learning, very similar to human-style learning. It's very useful for complex environments. So you have this idea of a grid world, and you're trying to maximize your payoff. You can take some action. Maybe I go this way, maybe I go this way, maybe I go this way. I choose to go this way, then I choose to go this way, -1. And then next one, I choose to go this way, 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 -1. And then I choose to go this way, choose to go this way, choose to go this way, choose to go this way. Now n+1. So this is an economic agent who's effectively maximizing utility. So it's sum, you can think of this as sum from t equals 1 to infinity of value of state, and then we probably, the state being each of these, we probably want the value of this state to be 1, value of this state to be -1, and maybe we want a discount rate so that the algorithm doesn't go on forever. So then your agents now, reinforcement learning, the power of it is they learn how to deal with this grid world. They learn how to optimize without ever seeing really any, without ever like seeing any rules of how the world works from you. So it's just learning how the world is working. So a Markov decision process consists of a 4-tuple: states, actions, probability of action, and reward of action. So S is the state space, P A is the action space, P of action is the conditional probability that action A in state S at time t will lead to state S prime at t+1, generally to assume to have the Markov property. What the Markov property means is that the probability of going from state one to state from state it's probably going from state 3 to state 4 is not the probability conditional on the probability. It's not conditional on the state you were in before state 3. So you only need to know that you're in state 3. If you have a state space, that should summarize everything. R of A of S comma S prime is the reward received from transitioning from state S to S prime due to action A. So this is a Markov decision process. You have different states with different probabilities to go between them, and you can choose actions that will allow you to have certain probabilities going between states. So if you're in S1, you can choose A0 or you can choose A1. If you take A0, there's probably 0.1 of ending back up in S1. If you choose A0, is probably 0.7 of ending up in S0. If you choose A0 is 0.2 probably of ending up at S2. And there's a if you choose A1, you get a 95% chance of ending up back in S1. So if your goal is to get this plus 5 and not get this -1, you want to keep doing actions that will, as much as possible, make it likely that you end up in positive states and not negative states. So this is an MDP. You have certain states and you have certain probabilities of going between states. And you have certain rewards when you go between certain states. So valuation is a common both dynamical economics and reinforcement learning. Valuation is a model-based method to find the value of being in a particular state. So how do we know how valuable it is to be in this state versus how valuable it is to be in this state? How do we know which state is more valuable? On the surface, we probably think it's more valuable to be in this state. But how do we know? We do what's called temporal difference learning or valuation, where basically we're over time learning how to adjust the value functions. We start off with this value function, value of each state. And the value of being in the state is the maximum with respect to the actions of the sum with respect to S prime of rewards plus the value of being, or sorry, the maximum with respect to the actions of the possible states tomorrow, of the probability of being in states tomorrow, of rewards plus the value of being in state tomorrow. So you have rewards of tomorrow's state based on the action, and then you have the value of being in state tomorrow. So you really want this value to be high, and the value is higher the more this the future rewards are high. This is big in macroeconomics because it allows you to think about, well, how do we create a function that maximizes long-term value without having to think about every single state you could end up in, but just thinking about the value of the state tomorrow. So one way that we do this is what's called Q learning. So the new Q value, which is the value of an action in a state. The value function is actually the maximum of the Q table. The new Q value is the former Q value. New Q value is the former Q value plus alpha, your learning rate, times R, the reward of that state, plus gamma, the gamma, which is the probability of experimentation, the max of the new action, times the value of the new action minus the original value. So this is really big in macroeconomics. Game theorists are getting more into reinforcement learning. How do you learn new states? You experiment. This is the experimentation exploitation trade-off. You have the idea of multi-armed bandits. Multi-armed bandits, you have the idea that you have this casino. There's a bunch of different slot machines in the casino. You're pulling on each of the slot machines. They have different distributions. Maybe one of them pays off really well, and then it never pays off again. So you want to figure out how do you get the best payoff from each of the slot machines. We want to exploit and you want to experiment. Sometimes you're going to pick the best slot machine. Sometimes you're going to pick a slot machine that is new because you want to figure it out. So that's the multi-armed bandit problem. Economists have spent a lot of time on this, and it's becoming very important in computer science. Companies like Meta spend a lot of time thinking of how do we experiment with multi-armed bandits to get people to click on our things. Here's another representation, exploration, exploitation trade-off. Exploration, trying random actions in order to find more information about the environment. And then exploitation, using known information to maximize the reward. So over time, you want to exploit more as you learn more about the environment and you learn what's good and bad. Here's an example of a Q table. You initialize it basically to 0 for all states. And then over time, you learn that some states are good, some states are bad. And then there's some states where you have actions you would rather choose. So in state 499, you'd really like to choose action west because it's more likely to get you a better payoff in the future and higher rewards. Here's grid world with Q value. After 5 iterations, you learn you really would like to be in this square with the 1. That's a really valuable square to be in because that's high rewards. You don't so much want to be in the square with a -1. And you really, so if we're thinking about the actions that maximize the Q value, well, we start off, we look at 0.27 versus 0.22, you choose 0.27. Look at 0.51, which is our only option, 0.72, 0.84, and then 1. So you want to maximize your value. You want to take the path that maximizes your value. Why is this square less valuable? Yeah, you could still, if you wanted to, go here, here, and then go here. Even though you don't want to reach the -1, you can still get the 1. Well, there's still a probability that you learn that you could end up in -1. And also, it takes longer to get to that 1. So there's a cost to waiting that you internalize through a discount factor. So moving on to the idea that neural networks are eating the world, deep Q learning is at the forefront of reinforcement learning, combines neural networks with Q learning to more efficiently map the Q function. Allows for significantly more dimensional state spaces. This is the primary way that neural networks are invading economics, is by basically creating ways to more efficiently map a value function. What is a value function in macroeconomics? What is a value function in all of economics? It's a high dimensional function of many variables. And the more quickly you can map that, more efficiently you can map that, the better you can do. In game theory, we have algorithmic decision making, very similar to reinforcement learning. In IO, we have algorithmic pricing, where you've seen some reinforcement learning papers. In macro, you have dynamic optimization tank models. We already talked about the final review. And then in terms of open source data, I have a bunch of links here to a bunch of data. If you're interested, you can take a look. Words, common surveys. Thank you. That is the end of the last recitation of the class. Do you have any questions?
No, I mean, yeah.
All right. Well, thank you for coming. Good luck on the final. And yeah, if you ever need anything, just let me know.
Yep, I got you. Thank you, Dana. I appreciate it.